Today, we're going to pull back the curtain on the hidden science that pretty much runs our world. We're talking everything from how airlines schedule their flights to how investment portfolios are built. And believe it or not, we can start to understand it all by asking one very simple question.
Right, let's get into it. Imagine you're making a meatloaf. You want it to be good, not too fatty, but you also don't want to break the bank. Well, this isn't just about cooking. It's what's called an optimization puzzle. So let's break this down like an engineer would. Our objective? Super clear. Spend as little as possible. The decision we've got to make is the ratio, right? How much beef versus how much pork. And then we've got our constraints, which are basically the rules of the game. The final weight has to be 1 pound, and the fat can't be more than 25%. Once you have the cost and fat data for each meat, well, you've got all the pieces of the puzzle.
And would you believe it, just by thinking through that meatloaf problem, you've actually used the fundamental logic of a really powerful field called operations research. It's literally the science of making the best possible call when you're working with limits.
Okay, so we've kind of backed our way into this science of best, but what is it really? Let's get a proper definition.
Operations research, or just OR for short, is a pretty simple idea at its core. It's all about using scientific, data-driven methods to help people in charge make smarter choices. Think of it as a way to replace gut feelings with a structured analysis to find the absolute best way to use what you've got, whether that's money, materials, or even just your time.
But the story of OR doesn't actually start in a business school or a factory. It starts on the battlefield.
So during World War II, the British military leaders got this unique team together, and they nicknamed them Blackett's Circus. And it was this wild mix of physicists, mathematicians, and other brainiacs. Their job? To use pure math and logic to solve really urgent military problems, like what's the most effective way to hunt for enemy submarines, or how can we best deploy our radar systems? They were literally researching military operations, and, well, the name just stuck.
So after the war, all these powerful techniques made the leap from the military right into the business world. And why? Because the post-war industrial boom was creating problems so big and complex that the old methods just couldn't cut it anymore. Suddenly, managers needed better tools to handle massive supply chains and complicated production schedules. And then, computers came along. They could crunch the huge numbers needed, and OR just exploded. It became absolutely essential for almost every major industry out there.
So, how does this stuff actually work? Well, the secret is all about translation.
You see, the real magic of operations research is in something called modeling. It's the art of taking a complicated, messy, real-world situation with all its confusing bits and pieces and translating it into a clean, logical, mathematical puzzle. And once it's a puzzle, you can actually solve it.
And this isn't just random guesswork. It follows a really strict scientific method. First, you have to clearly define what the problem actually is. Then, you build a mathematical model to represent it. You feed that model with real data, and then you start manipulating it to find the best possible solution. And finally, you test that solution to make sure it works and put it into action. This structured approach is what makes OR so incredibly powerful and reliable.
And the analysts who do this have a whole toolkit of models to pick from. Now, mathematical models are definitely the most common, but they can also use simulations to imitate how a system behaves, or even build physical models to represent something like a factory floor. The real key is just choosing the right tool for the job.
Okay, so now let's look at the most famous, most widely used tool in the entire OR toolkit, something called linear programming. Let's dive into another classic problem. Picture a furniture maker. They want to maximize their profit from making 2 different screen models. Now, each model brings in a different amount of profit and uses up different amounts of their 2 limited resources, wood and time. So the big question is, what's the perfect mix to produce?
And this is how we translate that real-world problem into the language of math. Now, seriously, don't let the symbols freak you out. X1 is just the number of Model I screens we make, and X2 is the number of Model 2s. That top line, our objective function, that's just a fancy way of writing the total profit. And the 2 lines below are our constraints. They're just math sentences that say, hey, the total wood we use can't be more than 6 units, and the total time we spend can't be more than 28 hours. That's it.
Now, to solve this, you can actually draw those rules on a graph, and the area where they all overlap is called the feasible region. Every single point inside that shape represents a production plan that's actually possible. It doesn't break our rules about wood or time. But here's the thing. We don't want just any solution, right? We want the absolute best one.
And here it is.
This is the crucial insight. There's this beautiful mathematical rule called the linear programming theorem, and it proves that the optimal solution, the one that gives us the most profit, will always be found at one of the corners of that feasible region. This is a total game changer. It means instead of checking an infinite number of possibilities inside the shape, we only have to check like a handful of corner points.
And this is the power of the method in action. After checking just those few corner points, the answer becomes crystal clear. To maximize profit, the furniture maker should make 3 of the high-profit Model I screens and 0 of the Model 2s. This exact mix gets them the absolute maximum possible revenue, $360. No guesswork, no intuition, just the single best answer found by math.
Now, linear programming is incredibly powerful, but OR has even more specialized tools for different kinds of puzzles.
For example, what happens if you can't have a fractional answer? I mean, for the furniture maker, building half a screen is totally useless. That's where something called integer programming comes in. It adds one more simple rule. The answers have to be whole numbers, and that's absolutely essential for problems involving things you can't just slice in half, like people or machines or cars.
And the toolkit just keeps on going. There are transportation models, which are kind of like Google Maps for a whole fleet of delivery trucks, finding the absolute cheapest way to ship goods. There are assignment models, which are designed to perfectly match people to jobs to get the most done. And then there's dynamic programming, which tackles these really complex problems that happen in stages, where every decision you make affects the next one, like planning an investment strategy for the next 20 years.
So why does all of this matter? Well, because these tools aren't just for textbooks. They are quietly, efficiently, and constantly running the world all around us.
You know, every time you book a flight, OR algorithms have created the schedules and assigned the crews to keep costs down. When a package lands on your doorstep, OR has figured out the most efficient delivery route. This science is scheduling factory production lines, it's building the optimal investment portfolios for our retirement funds, and it's creating staffing schedules for hospitals so that enough doctors and nurses are always on duty. It really is the invisible engine of efficiency that powers our modern world.
And that leaves us with a final thought. The core principles of operations research, figuring out your goal, identifying your limits, and then finding the best path forward, those are universal. You can apply them to just about anything, from planning your weekly budget to figuring out a complex project at work. So the question is, what's the next big optimization puzzle that you're going to solve?